Right. Okay, so I think last lesson, right, we just wanted to discuss two questions. We didn't really have time to discuss these two. So today we're just going to cover that first, and then we'll move on to what we actually need to cover today. Okay, so if you never tried the two questions, it's fine. I'm just going to cover the concept again. Okay, so I think this was page 40. Last lesson, we discussed intermediate bonding, right? Okay, what does that mean? So molecules, what we have, the takeaway from last lesson is that most molecules have a mixture of both ionic and covalent, right? Okay, so that's like a mixture. So usually here we are just trying to determine how much ionic and how much covalent is there in one compound. Of course, it varies for different compounds, right? And we have taken a look at a few factors. If we look at this first question, we are not going to write down the answer yet. Okay, let's break it down. We are asked to compare these two structures, NaCl2 and NaCl, right? So what is the factor that we're trying to compare in this question? What is the thing that we're comparing? Okay, we're looking at the cation ion, right? So the cation ion, we must focus on the charge density. In other words, okay, so you just have to spot yourself. I think this is quite easy. The charge density of the cation ion will affect how much ionic versus covalent character there is in the structure. Okay, we look at the rough idea first. It deviates more from the ionic model. Can you all recall what the ionic model means? What are they trying to say in simple terms? The ionic model assumes that it is 100% ionic. Yes, and we already know that that is never the case. It is usually a mixture. So if MgCl2 deviates more from 100% ionic, it means it is more what? MgCl2 has a higher covalent character, yes. Okay, so the little diagram that I love to use, right, to kind of see this, I like to draw a line. And this line, right, it represents MgCl2. Versus NaCl2, I have the same exact line, but this is kind of like a spectrum, right? MgCl2 has a higher covalent character because it's what I say, right? So it has more covalent character. You imagine this right hand side here has more covalent character. And NaCl is much less. So in other words, you can think of it as proportions. Out of 100%, okay, how much ionic and how much covalent character there is. So in this case, I'm sure you all can see MgCl2 has quite a great deal more covalent character as compared to NaCl. And it makes sense, right, guys? Because percentage is out of 100%. If you have more covalent character, it means you are less ionic, vice versa. Okay, so with that said, right, okay, I think the explanation is really better. I'm just going to quickly write down the point form and then we can move on already. So it's quite clear over here. You must talk about Mg2 plus. But let's not go straight into charge density just yet. I want you guys to always mention remember, you all remember charge density is proportional to what? Very important concept. It's not just charge, but it's also dependent on its ionic radius. Okay, so it's Q over R. You talk about both factors first. Mg2 plus has a higher charge, but how about ionic radius? Oops, higher charge will be. It has a higher charge, but yet smaller ionic radius, right? As compared to Na plus. Okay, and because of that, you can then conclude that Mg2 plus has a higher charge density, which means higher one. What's the next keyword that we need to discuss? Okay, so I've explained the whole process of how you have a lot more covalent character than another compound, and it's because the cation ion itself has a higher polarizing power. What does polarize mean? Once again, later, right, in today's lesson, I'll talk about what polarize really means. Okay, but it's time to polarize the what? Okay, Mg2 plus polarizes the electron cloud. Good. Okay, again, you have to polarize an electron cloud, not a particular atom or compound or whatever. Polarize the electron cloud of Cl minus to a larger extent. Remember, it's trying to cool the electron cloud of the electron. If there's more polarizing, that means there's more what? The degree of sharing has to be higher, right? So there's a higher degree of electron sharing. And as a result, higher degree of covalent character. It all links up very, very nicely. Okay, try not to jump your answer straight to covalent character. Because we have to talk about sharing first. It's all about the sharing, right? That's why you have more covalence. So personally, what I like to use to interpret questions like this, right, is I imagine a line. The line has to be the same for both because it's always out of 100%. It's about how much percentage is allocated to ionic and how much percentage is allocated to covalent. We take some marker. Okay, now I don't really need to discuss the second question because it's pretty much the same thing. So generally speaking, right, this concept it's not it's a little bit difficult to understand at the start. Okay, but once you understand already, right, the questions are very simple in that sense. Okay, there's another side of chemistry, right, where the concept is very simple, but the questions can be very crazy. Yeah. Here, a lot of application. Here, there's not much application. So I guess this is like a better version, okay, of questions that will come up. But anyways, you can discuss the same thing, right, for the next question. The answer is roughly going to be the same, so I'm not really going to like write the whole thing out again. This time around, we are asked to discuss AGI and AGF, right? What is the factor that we are supposed to compare in this case? Okay, here we need to look at the anion first, right? So here, in this question, we have to look at the ionic radius of the anion. Once again, I already explained last lesson what it means. Okay, but ionic radius of the anion in this case, right, just need to look at the size, right? I minus versus F minus. So what did we recall last lesson? The larger the ionic radius, what does it mean? Okay, so it's further away, so that means it is more easily polarized. Okay, you don't have to say the further away part. So let me just tell you what to write in the exam, what's necessary. The higher the ionic radius, okay, the anion's electron cloud, we specified, is more easily polarized. Again, try not to ever forget the word electron cloud. It is incorrect to say you polarize the anion. No, it is the electron cloud that gets polarized. So just these two keywords will do. You don't have to tell me it's further away. The further away part, right, I discussed because you all should, it's to make you all understand. Okay, but anyways, it is more easily polarized than these. The degree of sharing has to be higher again. So higher degree of electron sharing means higher degree of covalent character. Once again, like the last sentence, right, you notice it's pretty much the same thing, right? Roughly, I think this anion, right, the answer is a lot easier to explain because it's a lot shorter. Just tell me about the size. Larger size means more easily polarized. We jump straight to that. You don't have to tell me that's further away or whatnot. If you were to look at that diagram once again, if you were to draw out AGI and AGF, okay, how will it look like? AGI deviates more from the lattice energy, right? So it is more covalent. In other words, this is the covalent side. AGF has a lot less covalency. If you are more covalent, it once again means you're less ionic. Less covalent means you're more ionic. So it goes both ways, obviously. Okay? You could say one compound is more ionic than the other, or the other compound is more covalent than another. Right? As we mentioned, this is the reality of bonding. It's always a mixture of both. Any questions so far? Okay, good. Okay, so once again, this question, when it comes to an exam, just make sure you know the keywords to answer this. Not much application, so I would say that pretty much stops right there. Anyways, any questions? If don't have, we shall move on to page 4. Wow. Right, okay, so agenda for today. Okay, so agenda for today, right, is we're going to look at this new thing called, okay, not say new, okay, but we're going to look at intermolecular forces of fractions. Okay, that's the title of this segment. And this is essentially the last segment of the whole story. It's probably the happiest segment. So I would say, right, guys, as we go on into more topics, Chem bonding mostly lies in this segment already. Yeah, like slowly, like you can tell dot and cross and all that, right, start to phase out. Okay, not say phase out, they will still be tested, but not as often. But then they will more or less test basically on intermolecular forces. Okay, but anyways, okay, to get into the meat of things, right? From now on, I'm just going to call it IMFA because it's really quite a lot to say. Okay, so intermolecular forces. So the word intermolecular means what? Okay, good. Between molecules, right? Let's get the idea straight first. Let's look at a simple diagram. I'm sure you guys know that this is carbon dioxide. Okay, this is only one carbon dioxide molecule, but is that it? No, right? There are millions of carbon dioxide molecules in the atmosphere. So you think about it, okay, this is a circle structure. Okay, you might want to ask yourself what this structure means. But I'm going to draw another carbon dioxide. Once again, this guy has this outline. What does this outline represent? Any guesses? We mentioned this keyword just now, actually. Okay, so just take note from now on, whenever I draw like this outline, right, is what you should visualize in it. This is an electron cloud. What is an electron cloud? Okay, sounds crazy, right? No, actually, it is just the region where there are electrons. That's it. So for carbon dioxide, this little cloud over here is where all its electrons lie in. That's pretty much all that means. So that means outside of this electron cloud, you can't find anything lah. Okay, it's only within this electron cloud you can see all of its electrons. Make sense? Okay, so we're going to use these circles to represent electron cloud. Now, for intermolecular forces, what I'm concerned with, right, is the interactions between these two molecules. So let's draw this inside. Label this. This is your intermolecular forces. Why I'm doing this is because I do not want you guys to be confused with covalent bonds. Now, in today's segment, right, our main focus is on simple molecules. Okay? And simple molecules and covalent bonds, we all know that, right? But we are not discussing the covalent bonds today. Our focus is on the intermolecular forces for quite a lot of reasons, actually. Because, guys, take this down. Intermolecular forces helps us to explain physical properties. In fact, guys, in a lot of the times, right, I will mention this during lesson. I will tell you guys why we are learning certain topics. Why all the topics are all linked together. Okay, like eventually we're going to learn this thing called reaction kinetics. It's about the speed of a reaction. Here we are far from that. Right now, we just want to know how to explain why different compounds are solids, liquids, or gases, stuff like that. Okay. Anyways, what are physical properties? Let's take down some examples. We'll be looking at melting points or boiling points. That pretty much is around the same thing. But the more important one we're going to learn, right, new in JC is solubility. Okay. We're going to understand how solubility works. Like why is oil not dissolvable, not soluble in water, right? It's because of intermolecular forces. Basically, how molecules interact with one another. Make sense? Okay. So with all this said, we have to understand, right? Intermolecular forces, they are actually rather weak. Like I'm saying objectively. Objectively, intermolecular forces are weak, and hence it can be overcome. Like in general, right? You can break intermolecular forces. That's why we use that to explain melting and boiling points, for example. What we are not concerned with, right, are covalent bonds. Because I want you to think, right, covalent bonds are indeed very strong. I feel that a lot of people have this misconception. When they see simple molecules, they think that the covalent bonds are weak. Then when they see giant molecules, the covalent bonds are strong. No, that's wrong. Okay, covalent bonds in general, doesn't matter what structure, is always very strong. So guys, let's say I have water molecules. Let me just draw two water molecules here. If I were to boil water, think about it. What am I doing when I boil water? Liquid water turns into gas. Now, when I boil water, am I breaking these covalent bonds? Am I basically killing the water molecule? No. Gas is still water, right? What I'm actually breaking is what when I boil water? Yes. I'm trying to break these intermolecular forces here. Because when I break them, right, that's why gases are very far apart. You don't have this intermolecular force to kind of pull them into place. So that's the idea. We are never ever breaking covalent bonds. I really need to drill this idea in you guys right now. Okay, we are only discussing intermolecular forces in this context. Same thing for carbon dioxide. We are never ever breaking the double bond. I mean, double bonds are very strong, right? Okay, you can't break that. So just to date all the way back to the first chem bonding lesson, I discussed structure and bonding with everyone. Now, guys, in exam questions, they will always ask you guys to refer to structure and bonding. So let's try to answer this little two-step process. If I were to give you carbon dioxide, what's the structure of this compound called? Simple molecules, what's the structure? It's just simple molecular structure, right? Okay, so that one not really my case. Okay, so take note. We have learned giant ionic, we have learned giant metallic. Now we are basically today going to focus in on simple molecules. Now I'll ask you a question, right? Can you remember? If the structure was giant ionic, the bonding is called what? What kind of bonds? Ionic bonds, right? Giant metallic, the bonds are called metallic bonds. Very simple, right? Okay, but over here is a bit different. When there's any bonding for simple molecules, take note, you must specify the intermolecular forces of attractions. I'm going to spell out the whole thing because it's that important. This is what you should be telling me here. I know they say bonding, right? I know intermolecular force is not a bond, but that's what you need to write it to fulfill this criteria. You cannot tell me covalent bonds. This is not wrong, but just not relevant to what we are discussing. Why can't we write covalent bonds? Why not? Because I already mentioned, anytime to do with simple molecules, all its physical properties can be explained only via intermolecular forces, not covalent bonds. So mentioning this is not wrong, but just not relevant to the question. You will not get your mark, basically. Okay, this is what affects its physical properties, and this is what we want to study. That's why this right here is what you mentioned. So take note of this first. As we do more questions, I will reiterate this point more and more. Okay, so far. Okay, so I spent quite a great deal on this page. Okay, there's a lot of stuff to write. Okay, anyways, you can turn over to this. Where are we? What's that box there? Oh, okay. I mean, the difference is basically what I explained already. I don't even have that box. Okay, but I explained already, right? Okay, anyways, yeah, the box you just arrow to whatever I just discussed here. Okay, anyways, turn over to the next page. This next page here says, right, IDID attractors. Okay, what's that first? We're gonna slowly dive into the molecular forces. Let me list down first. Today we're gonna cover 3 types of intermolecular forces. Now I'm gonna write the short form first. Later then I'll explain the full form, basically. Hey guys, do you all remember what intermolecular forces you all learned in secondary school? Can remember the names, the weird names. Have you heard of the term dispersion forces? Okay, never mind. Have you heard of the term van der Waals forces? Yes. Okay, so all that is basically going to change names in this context. So let me write down all the different types of intermolecular forces. Now just take a look at the names first. I'll cover sequentially, so 1, 2, then 3. But hydrogen bonding, right? I know, guys, you'll be like, what? Why is there the word bonding in hydrogen bonding? Never mind, later I'll talk about this. I don't know why they name it like this as well. Okay, but to not cause any confusions, once again, I am done with covalent bonds. All of these guys are intermolecular forces. Okay, I know there's the word bonding there. I also don't like it, but no choice. Anyways, let's talk about the first one. Now, the first type of intermolecular force is called IDID. Now, the full name isn't really written there yet, so perhaps let's write this down. Okay, it's called instantaneous dipole dash induced dipole. Now, in exam, you can just write IDID attractors. Okay, if let's say your teacher is a bit strict, right? You guys can write a full name once in your paper. Then the rest you can just write IDID, like bracket, then you use it for the rest of the factors. Okay, but I'm a bit lazy, I'm going to use IDID from now on. Okay, but anyways, you cannot ignore the name, okay, because we need to know how this interaction comes about in the first place. Let me look at the first 2 bullet points. Okay, I'll talk about this eventually. It is the weakest. We start off with the weakest attractor. Number 2, right? Okay, it exists in non-polar molecules. This is what is already printed in the notes. Yes. However, I need you to add something, right? This second one has a little disclaimer. Okay, and the disclaimer is this: all simple molecules have IDID interactions. I know now it's a little bit like what's going on, right? Never mind. Okay, later on we will see what exactly I'm referring to here. Okay, so let me repeat myself as you're writing. All simple molecules they have a fundamental interaction. And that is called IDID. So it's the fundamental ones. The rest later we will discuss. Okay? Now the statement here is not wrong, but it's just not complete. Yes, primarily we are looking at non-polar molecules to explain how this comes about. So guys, let's recall what is a non-polar molecule. Can you tell me? It is a molecule without any overall dipoles. Good. Okay, so that dates back to our electronegativity concept, right? So once again, a non-polar molecule has no overall dipole moment. Perhaps it's probably because it cancels out, right? Or perhaps there's just no dipoles at all, like it's not even polar. Like doesn't even have polar bonds. It doesn't even cancel out all the time. But anyways, that's what I'm discussing. Guys, let me ask you a question. The electron cloud of a non-polar molecule. I give you all two options. Do you think the electron cloud is symmetrical or asymmetrical? Think about it. No overall dipole. So is it symmetrical? So a very nice symmetrical oval shape. Or is it asymmetrical? Means it's not evenly distributed. Asymmetrical? No, not exactly. Okay, guys, take a look again now. If there's no overall dipole moment, that means the electrons are not going closer to any atom, right? So a very, very simple example is CH4. Guys, in CH4, we have a CH bond, right? Is CH bond polar or non-polar? Can you remember? Yes, okay. CH bond is non-polar. Basically, the electrons are not going closer to the C nor the H system. So is there any uneven distribution of electrons? It's very even, it's very fair, right? So once again, is it symmetrical or asymmetrical? Symmetrical. Okay, good. Okay, so I'll bring you guys through this again now because it's a new concept. Electron cloud is symmetrical. Later on, we'll see what terms we're going to finalize. There's a lot of ways to explain this. Okay, but if you guys forget the term symmetrical because you're not very comfortable with it, okay, just bracket. Symmetrical means evenly distributed. I think this one some of you guys may prefer. Okay, so either one works now, honestly. So I repeat myself, why is it evenly distributed? Why are the electrons so evenly distributed? Because it's not unfair, right? It is a very fair distribution of electrons. They're all carrying it. It's not going closer towards one atom. Okay, so if it's very symmetrical, we will see an electron cloud that looks something like this. Very nice circle, right? Asymmetrical means, right, maybe it looks very odd like this. Can you see the electrons are distributed towards the right-hand side? This is later what we'll discuss. Anyways, okay, any questions? Okay, so how is this going to lead to ID attractions? Okay, guys, can you all look at the box? This box is very crucial. How do ID attractions arise? Okay, let's not just write words inside, let's draw a diagram. As I mentioned, electron cloud is symmetrical for a non-polar molecule, correct? So let's draw a very nice even circle. Okay, this is one molecule, agree first, the electron cloud. Now I'm going to draw another guy. Okay, because it's not just one guy, right? It's multiple. Okay, do you think they're going to have any interactions with one another? Are they going to attract each other? Okay, some of you will say yes, some of you will say no. Okay, never mind. Right now, right, you have to answer one question. Are electrons stationary or always moving? Okay, electrons are always moving, right? They're always like flying around. Okay, because they are always moving, it's never ever going to stay symmetrical forever. Does that make sense? It will, at any point in time, at any instance, the electrons might suddenly become unevenly distributed. So I say again, electrons are always moving. At any one point in time, it might decide to be uneven. So guys, what happens over here? Can you all remember the partial charges? Where do you put the partial plus charge? Partial positive. Okay, where should you put your partial positive charge? Okay, first where are the electrons gravitating towards? The right. So that means if the right has more electrons, it must have a what charge? Negative, yes. So it has a partial negative charge. Not an actual negative charge because it's not actually giving electrons away, right? It's not an ionic compound. Okay, we're not talking about ionic in this case. It's all about simple molecules. Okay, just to come back to this again now. There are less electrons on the left, so there is a partial positive charge. So can you all see, guys, this was created out of nowhere. In other words, the word instantaneous. Okay, what does the word instantaneous mean? It means that it is created on the spot. Okay, like simple English, created on the spot. Suddenly created. You can think of it that way. 1 second ago, it was perfectly symmetrical. And because electrons are always hyperactive, right? They're always moving. The next second, suddenly it moves to the right too much. So at that very moment in time, it created an instantaneous dipole. This right here is a dipole with charges. Okay, so I mentioned again, initially, okay, there are no interactions. Okay, because you have no charges, right? If you have no charges, okay, what interactions can you form? Nothing. But 1 second later, it suddenly formed a dipole on the spot, instantaneous, created in like 1 second. Does that make sense? Okay, so you really need to know what instantaneous means. The whole time, like the whole of my JC life, I didn't even know what that means. Until they tested me in A levels, and this was the exact question. So our batch, like kind of like half of the batch, didn't know how to answer this. Okay, that's why they're teaching this right now. Okay, anyways. Guys, if there is a negative on the right-hand side of this molecule, what do you think will happen to the guy on the right? How would the guy on the right here react? If there's a negative here, that means there's a lot of electrons, right? And electrons tend to repel. So can you see the electrons on the left of this guy? He's like, oh shit, why there's so many electrons? Time to leave. So it's going to go towards the right-hand side now. So do you notice what's happening? When there's too many electrons, like you see a crowd coming, what way? Go and join the crowd? Probably not, right? You want to go away from the crowd because I don't like crowds. Okay, so what I'm going to do now is a lot of people will also, Singaporeans don't like crowds, right? Okay, so they see a lot of people coming, they'll just, okay, time to leave. And this carries on indefinitely. Can you see that? It keeps on going for the next molecule. And that's how every single one of them now has interactions with one another. A partial negative and a partial positive. This right here are your interactions. We call them ID interactions. Okay, slowly take in the whole process. This is how it works. Okay, now I haven't written down any explanation yet. Okay, but perhaps you guys want to take down the word induce. Do you know what induce means? I induce change in the country. You know what that means? Is to create change, right? Is to cause change to happen, to enact change. So it's like, okay, a bit of English here. So induce means to create a dipole in the neighboring molecule. So the first guy formed a dipole on the spot, instantaneous. And this will cause the rest of the people to create a dipole in themselves. One guy changed, everyone changed. Okay, does that make sense? One guy started it all, started a chain reaction. Now every single one of them has ID interactions. Try to visualize the mental picture in your head. How did all this happen? Anyone still not sure about the meanings yet? Instantaneous and induced. Okay. Okay, so I'll bring you guys through this. Now we're going to write the explanation. I'm going to write it down in blue over here. Okay, so first you must tell me, right? As electrons are always moving, we start off at the start. We start off at the first compound, sorry. As electrons are always moving, the electron cloud may be polarized at any point in time. Just take a look at the phrasing that I'm using over here. Electrons always moving, it will be polarized. Now, I will use the word polarized because we kind of covered this earlier. Polarized means to make it not evenly distributed, to make it asymmetrical. Okay, so this is not polarized, this is perfect. And then now it's polarized because it's not symmetrical. I use the words any point in time to convey the word instantaneous. Okay, so you can just, the next sentence, you can just say, this creates an instantaneous dipole. Okay, hello, Alice. How are you? Have you recovered? Nice, very nice, very nice. Okay, and once you create an instantaneous dipole, this will cause everyone else to have a dipole, correct? So let me finish out the sentence first. This will induce a dipole in a neighboring molecule. That is the end of this explanation. Okay, so the word induce is also used here. Okay, so you can do that as well. So explaining the instantaneous part is a bit longer, the induce part is a lot shorter. You just move. Okay, think of this first. Okay, so I recorded like the first part of the lesson. Okay, you can look through that because it's one whole segment. I'm quite more. Okay, as of now, right? Okay, you know what van der Waals forces? Have you learned? Okay, it's pretty much similar. Okay, but now you just change it from van der Waals forces to call them IV attraction. Okay, for now you just need to know that it's similar to van der Waals. Yeah. Okay, as for the detailed track, you can just look at the video or later I can explain. Okay. Okay, so we are on page 41, and let me just tell you about 40 first. Okay. Later page 40, maybe you can copy from there because it's erased. For this box over here, right? Basically just copy out from here to here, including this diagram. All right, so there's a lot of details over here. Non-polar molecules initially had nothing, and then one guy just had to have a dipole created in the instance, and then everything else will follow. Okay, so that's the origin of this. They might test this as well, right? Okay, and with that said, we are going to proceed over to the different factors affecting its strength. Okay, anyways, when we look at an interaction, right? Okay, this is the origin, but how it's created in the first place. But now we need to look at its what affects its strength, right? So it's mentioned all over there, right? But let me just clarify a few things. Right, the very first factor that affects IDID is the size of the electron cloud. I'm going to write down the three words: electron cloud size. Now, this is a very, very important factor. I will discuss why later on as well. But for now, right, okay, so everything is mentioned there. How do we measure the size of the electron cloud? Some molecules are bigger, some molecules are smaller, right? So perhaps just go and note this down. How to measure the size? Just compare the MR of the molecule. Very simple, actually. Okay. So if I were to ask you guys a very simple example, if I have hydrogen gas versus carbon dioxide, take note of this example also, it's not in the books. Very simple example here, who do you think has a larger electron cloud size? Who's pretty much bigger? Okay, has to be carbon dioxide, obviously, right? Why? Why is carbon dioxide much bigger? How did you all compare in your head? Okay, the MR of hydrogen is 2, MR of carbon dioxide is 44, so this is very obvious, right? Okay, so from here, you compare the size of the molecule and you tell me who has stronger or weaker IDID attractors. Now, before I move on to the actual explanation, first of all, I need you all to take note of this, very important. This is the electron cloud size is the primary factor to compare. Meaning to say, whenever you are thrown two compounds, the very first thing that you must look out for is their size. Okay? If let's say the sizes are similar or the same, then guys, can we compare the size still? If let's just say the MR of one guy is 42, the other guy is 44, can we still compare the size? Not really, right? It's like very, very similar in size. So if you can't compare the electron cloud size, then we will look at other factors. Later we'll discuss what the other factors are. But for now, let me just reiterate this point. Electron cloud size is the number one thing that should appear in your head when you're asked to compare the strength of the ID attractors. Okay, first? Yeah. Okay, so how does electron cloud size lead to different strengths? Okay, so imagine this, guys. The larger the electron cloud, are you going to be more easily polarized or less easily polarized? Okay, we discussed this in the previous segment on intermediate bonding. The larger the electron cloud, that means you are further from the nucleus, right? So if you're further from the nucleus, it means you are more easily polarized. You're less attracted, right? Yeah, okay. So let's write out that idea. Larger electron cloud means valence electrons further from nucleus. And when you're further from nucleus, it means less attracted to the nucleus. And just like what we learned in the previous segment, less attracted means more easily polarized. Now let me just show you guys what is necessary in your explanation. What you need to just tell me is this: a larger electron cloud means it is more easily polarized. You don't have to tell me about the other two. The other two is just to help you all see the connection. Once you see the connection, I'm telling you all just need to write these two keywords, because that's how you save time. The rest will not give you extra marks, so why write it, right? Guys, if you're more easily polarized, do you think you have stronger interactions or weaker interactions? I'm talking about this thing, the interactions between two molecules. So imagine this. Okay, now let's draw in a simple diagram to help you all visualize. I have a very small molecule. Now, a small molecule, is it easily polarized? No. So maybe the polarization is like a bit. Yeah, draw small. Okay, so the interactions are between these two molecules. Okay, so that is your ID attractors. But imagine a very large molecule. A very large molecule is super polarized, right? So can you see which one, right, has a greater difference? Who is more polarized? Clearly this one, right? So imagine this, the charges here are super big. Super large charges. Because it's very different from each other, right? And when that happens, the interactions here, is it bound to be stronger or weaker? Definitely stronger, because the charges here are a lot different from each other, correct? Because it's more polarized. The idea that we discussed in the last lesson, when we discussed intermediate bonding. A small molecule is not that different. So the charges very, very small, nothing much. So that's the connection over here. So let me write down the keywords. Larger electron cloud is more easily polarized. And finally, you can just tell me it has stronger ID attractors. You don't have to spell the whole thing. Okay. Again, this diagram don't need copy again. We already did it just now. Okay, this is just for your list. Okay, so this is a very abstract concept, because the reason why people struggle with this is because you can't see interactions. So in their head, right, it's just a blank space. They have no idea what they're doing. So I try my best to show diagrams like all this, so that at least there's something in your head, right? Work off your answer with. Okay, if not, it's just a blank canvas. Then we can't do anything, right? Okay. So these are our answer points for exam purposes. Later we'll see how this is applied in the question. Because remember, intermolecular force is used to explain what? What I mentioned just now. The overarching idea for today's lesson. Intermolecular forces, we study them so that we can explain physical properties like the melting points, boiling points of certain compounds. Why is it that some melting points super high and why some so low? It's all because we study this intermolecular force. That's why these are, you want to think about how it's applied to a melting point context. Okay, not now. Okay, anyways, okay so far. Okay, once again, that's the most important factor, the size, just going to count the MR. But as I mentioned, guys, there's always problems with this. What if the sizes are similar or the same? Then we can't compare size, right? Obviously, we have to look at other factors. Now, the other factor that we have here, okay, is on the next page. Okay, so instead of the size, we can also look at this thing called surface area. So the surface area of the electron cloud also allows us to check. It allows us to check who is stronger or weaker. Again, when do you compare surface area? Anytime you want. Only when what? When the sizes are similar. When you are out of the first option, you jump to this second option, right? So this is the next best option. This is used for similar or the same MR. In what scenario will you see this? Okay, so let's take a look at a rather specific scenario. Okay, this is a very specific scenario. Okay, guys, have you all seen organic chemistry before? A little bit, right? Okay, so that's all we need to know. Anyways, guys, if I were to give you all this compound called C4H10, okay, this is an organic compound because it's made out of carbon and hydrogen, right? But you notice this C4H10 can be arranged in a few ways. Now, it could be very basic, a little basic page here, and then just arrange all 4 carbons in a straight line. Boring, right? Is there any other way I can arrange these 4 carbons? Anyone want to try? Okay, not so basic anymore, right? Okay, I'm a little bit more special. I can put 3 in a straight line, and then I'll just put 4 over here. Make sense? Now, I don't really like this example because even though it's simple, you can't really see the difference. Let me try the same thing. Okay, guys. First of all, this is molecule X and this is molecule Y. Can we compare electron cloud size? Can or cannot? Why cannot? The MR is the same, right? Both of them are this dude over here. The MR here is 58. Okay, go and calculate. Oh, so we can't compare size, we need to compare space area. Okay, so I don't really like this example, but I'll come back to this again. Let me showcase a slightly more interesting scenario. 1, 2, 3, 4, 5, 6, 7, 8. Okay, guys, imagine this. I have a 8 carbon molecule chain. It's very long, right? Now imagine all these carbons are like Lego bricks. I have 8 Lego bricks. You arrange them in a long line, right? Now imagine this. This long line, I'm trying to bring through the door, but it's too long, right? What should I do? Okay, assuming that I still need to bring all 8 pieces through the door. Okay, what can I do? It's too long already, right? What will you do to solve this problem? So that you can walk through the door with this thing. Sorry? 30, okay, let's just say vertically is also too long. Okay, okay, I should clarify. Okay, let's say turn vertically also too long. Then how? Yeah, why not stack it, right? I can't remove pieces, that's part of the rule. I need to bring everything through, right? Why not I start stacking it? So, how do I stack it? Any idea? Instead of putting all 8 in a stupid straight line so that you can't fit through the door, what is the most compact way you guys can arrange this? In a circle. Oh, actually, that's interesting. Okay, that's very interesting, but that one we will discuss in organic chemistry. In a circle, we will get a compound that eventually looks like this. Now, that's good. Okay, but that here is not what we're trying to drive at. Okay, but good, that's actually a very compact way. Anyways, this is probably the most compact way we can find. I can arrange only 4 in a straight line, but the other 4, I put it up, down, like this. Can you all see this is very compact? Instead of a very long line that I need to bring through the door, I now have a nice little like package that I can just very easily bring through. In other words, this is a lot more compact. And whatever I'm drawing right now is the electron cloud. Can you all tell me who has a larger surface area? This I have to bring through the door, right? A lot of surface area covered. But now I have made it a lot more compact, so the surface area here is smaller. Can you see that? Okay, so this guy is what we call a straight chain molecule. This guy is what we call a branch molecule. When we learn organic for the first time in JC, then yes, we'll be looking at this again. We need to know how to branch them out. They are called isomers, if you can remember this term, where they are the same exact 8 carbons, but I can arrange them in different ways. This is only one of many ways I can arrange. The other way is like what Alice said, you can arrange them in a circle. That's also an isomer. We'll talk about that in the future, but this one they can test right here. So as I mentioned, guys, a straight chain molecule has a larger surface area. Take note. Okay, the larger surface area of its electron cloud. Not just the molecule, we're referring to the electron cloud. That's why I draw the circle. Branch molecules generally have a smaller surface area of its electron cloud. And with this explanation, right, we're going to look at one question right after this to see whether you all understand this idea. We can't compare size because they both have 8 carbons, but we can compare the surface area based on how it's arranged. So as I mentioned, guys, this is a very, very niche factor, only applying to straight chain and branch molecules. In other words, it means it's very easy to spot in exam. When you see 2 molecules that look like this, you already know how to explain this question. It's only here. Okay, so such questions are not hard because it's easy to spot what you need to explain. Okay, Ken? We're just going to go straight to a similar question to try this. So far, okay? I want you to turn over to page, if I'm not wrong, it's page 45. Basically, it's question 3 of the next couple of pages. Yes. Okay, take a look at this question here. Let's discuss together. Okay, since we have looked at this question already. Based on this question alone, just give it a read first. Who do you think has the, first of all, how should we compare this question? Should we compare the size or should we compare the surface area? Okay, just take a look at the structures a little bit. Ask yourself how you would explain this question. Okay, one thing you can do, right, is ignore all the H's. I know you're not very comfortable with organic yet. Okay, but never mind. Okay, just ignore all the H's. You'll notice that I ignore all the H's, this is what I'll get. And you can now, instead of using all the funky names that you use, right, just call them X, Y, and Z respectively. So that's easier for us to explain. Okay, guys, can we compare the size of the electron cloud for these 3 molecules? Okay, we can't because they all have 5 carbons. What should we do then? Okay, surface area, because this is a situation of branch and straight, right? Okay, who is a straight chain molecule? Okay, X. X is a straight chain molecule. How about Y? Okay, yes, as long as you have one thing coming out here is a branch molecule. Okay? How about Z? Okay, also branch. So you already know what's happening over here. Okay. So we work this out first, later we write down the full explanation. We have not space anyway. If you have a straight chain molecule, it's what? It has a larger, or in fact, now that we have 3 molecules, what word should we use instead? Largest, yes. Okay, comparative language, I must be careful. X is a straight chain, Y and Z are branch. So X has a largest surface area. I'm going to introduce another keyword you can use also. Largest surface area of compact. If you want to use the word compact, go ahead as well. If you don't like the word electron cloud, you can change it today. So if it has the larger surface area of contact, it means what? Yes, good. Guys, you all notice the more surface area you have, that means can you form more attractions or less attractions? More. Okay, so a lot of attractions, very, very strong. Imagine the surface area is like my fingertip. Very small, right? You can't form a lot of interactions. So obviously it's very weak, right? Okay, so the larger the surface area, it has the strongest ID attractions. Then who's next? That's the thing. Okay, so we are not okay. Let's not compare the rest yet. If you have the strongest ideally attractants, then what? Look at the question. What are they asking you to explain here? Okay, boiling points, right? Okay, boiling points. If he has the strongest attractions, that means what? Okay, highest boiling point. Wait, we have one keyword to link these two ideas together. Energy. Good. Okay, a lot of attractions, right? Very strong. You need a lot of energy to break it. And energy is in the form of heat. That's why boiling points come into play. To boil something, you need heat, right? Strongest ideal attractants, largest amount of energy to overcome, and hence highest boiling point. You see, sometimes you can write down your answer like this. It's a very good way of revising because you are literally just drawing a chain all the way down. A train of thought, basically. Okay? So I'll talk about the one guy that's straight chain first. Then now I compare between the two branch molecules. Okay, you all take a look at Y and C. Okay, never really thought about this yet, but who do you think, right, is, okay, we compare surface area. Who has the largest area? Okay, Y. Okay, so Y has a larger surface area because it is not as branched as Z, right? Z is more compact in a sense. So before we talk about anything, we can talk about Y first. Y is more branched than Z. Okay, so that's what you use to describe first. If you are more branched, that means Y has a larger surface area of contact. Do you notice how I've changed my language? I'm now comparing between the two guys, Y and Z. So you change it to larger. Okay. So if you have a larger surface area, it means, once again, more surface area, you can form more attractions. That's bound to be stronger. So Y has stronger ID attractions. Again, ID attractions are just the intermolecular forces. And since you have stronger attractions, you can just continue by saying which require more energy to overcome. So guys, can you arrange the boiling points in, they're asking for a decreasing order, descending order. How will we arrange this? Okay, should be quite simple, right? You explain everything already, then you conclude your answer. Also can. Okay, I know the question asks you to arrange first. It doesn't matter. You want to explain first, go ahead. In fact, I think it's better. You explain everything very nicely first, and then you rank the structures at the end of the day. Then you definitely will not go wrong. Okay, if you try to rank the structures first, that means you need to think the explanation in your head. Then a lot of mistakes will happen. Okay, so who is the highest boiling point? Okay, X. So you want to arrange, right? You can use the inequality sign. I don't know whether you have started that in math. Okay, inequality sign, X is higher than Y and Y is higher than Z. You can write X, Y, Z like this. Okay, so don't use comma. I know in secondary school you guys use this. Decreasing order, X, Y, Z. But this is not a good notation because how do I know if this is ascending or descending? Okay, so for descending order is like that. Okay, use this version from now on. Right? Okay, can. All right. Okay, so with that said, right, I think you guys are familiar enough to try questions 1 and 2. Okay, go back to the previous page. Let me see how you guys will try to explain this. Okay, we only talk about 2 factors. You decide which factor we should use. I only want to try this because I'm very particular about the keywords you have in this question. The keywords are what people lose marks in, not the understanding part. Everyone knows what this is all about, right? I'll write down the answer for part one in a bit. Again, always have another thing is try not to make your answer too long. If it's too much, it may reflect that like sometimes your teacher will just start to pick up more errors. And on top of that, there's a problem of time as always. Right? Okay, so let's look at the first question. It's that short. 2 bullet points can finish. Okay, I'm just gonna highlight the keywords which you should check for. Larger electron cloud is bromine, more easily polarized. They must come hand in hand. Okay, so because it's more easily polarized, you will form stronger ID-ID attraction, requiring more energy to overcome. As long as you have these small things, I don't care about anything else. Finish. Once again, make sure your answer is as concise as mine. This is the most concise it can be already. Okay, don't get tell me like, oh, this requires more energy to overcome the stronger idea. You're repeating yourself once again, which is a common problem that I usually see. And as for the second question, they're just asking you guys to predict. So who has a higher boiling point in this question? O2. O2 is obviously bigger by a lot. So it's the same exact explanation, except that you change lah. Now it's oxygen having a higher, larger electron cloud than H2, more easily polarized. O2 has stronger ID-ID attractions, same exact thing. Okay, if you notice, I gave 2 of the exact same questions to really help you all put it in. Right, Chem? Any issues here? Okay, so let me just recap what we have done in this segment. We have discussed ID-ID attractions. This is the intermolecular force, mainly for non-polar molecules. That's why for all the 3 questions that we have done, bromine, chlorine, hydrogen, oxygen, all the atoms are the same, right? So, as in terms of the molecule, OO, okay, there's no electronegativity difference, it's non-polar. But as I mentioned earlier just now, let me reiterate this one more time. ID is present in all molecules. All simple molecules, my bad, simple, have ID attractions. But non-polar molecules only have ID attractions. Meaning to say, guys, you can expect the next segment to look something like this. A polar molecule not only has ID, but it will have other interactions plus others. I put here plus others. So I mentioned this just now once. I want to talk about this again because Alice came in late. Okay, but anyways, very important. The fundamental interaction for all simple molecules is ID. But not like polar molecules will have others. Non-polar don't have anything new, just ID. Boring. Okay, this guy only have one item. Okay, take note of this first. Okay, now we're going to look at the next segment with this in mind. Okay. So this is just the first type of interaction. We have talked about non-polar. Now we're going to move into polar. Okay, so let's recap. You all remember what polar means? What is a polar molecule? Okay. A polar molecule is a molecule that has what? Overall dipole moment, yes. Okay, there is electronegativity difference. Okay, there is electronegativity difference. Let's give a few examples first. Okay. So of course we have stuff like HCl, okay, with HBr. You can see that the bond is clearly polar because the atoms are different and there's a difference in electronegativity. So these are polar molecules. You can even take a look at water. Water has oxygen, right? Okay, there's even nitrogen, ammonia, sorry. Okay, so many different polar molecules. All of them have a dipole. You can see that. And guys, we're going to look at the first one, right? We're going to look at the second type of interaction called the PDPD attractants. I'll write down the full name in a bit. But PDP attractions are for polar molecules. So I'll just explain what polar molecules are again. Meaning to say, a non-polar molecule does not have PDP. Whereas a polar molecule has both PDPD and what? ID, yes. So you all can see, must get this very, very straight. Because last time I also learned wrongly. Okay, they never clarify this. Your school will emphasize this also, don't worry. Okay, alright, I don't emphasize this. ID is like the base, everyone has it, right? Okay, but then you want to top up, right? You want to upsize. Okay, so for PD polar molecules, you have the extra PDP. That's why, right, guys? Okay, this will lead me to the next part. Okay, anyways, what page are we on? Okay, we're on page 46 now. Okay, not much over here, but let me look at the full name. PDP stands for permanent dipole dash permanent dipole. Yeah, same thing. A permanent dipole, permanent dipole. Earlier on, we discussed ID, instantaneous dipole, induced dipole. You guys want to make a guess why it's permanent? Now, polar molecules have a dipole moment already, right? Yeah, so that's permanent already there. So can you all see that? For a polar molecule, the electron cloud, is it evenly distributed or not evenly distributed? It's not, right? Because dipole means there's difference in electronegativity. Electron cloud is not evenly distributed. In other words, it's already polarized. So let's draw in a simple diagram. It's just like that. It's not evenly distributed. That's why you can see something like this, right? The left-hand side, there's a lot less electrons. The right-hand side has a lot more electrons. Because this guy is probably the more electronegative atom. Okay, you have another one of the same dude beside him. So the plus and the minus, because it's been here since the start, because the molecule is polar, this is your PDPD attractants. Okay. So I just want to bring back ID, because again, for the sake of Alice also. Okay. Just now, guys, when we look at ID attractors, did it already start like this? Okay, ID is for non-polar, right, guys? Does non-polar have this uneven distribution? Okay, no. Non-polar has no difference in electronegativity, so it's a very nice, evenly distributed electron cloud in contrast to this. Can see that? But it doesn't have interactions now. What happened just now? How do you get the interactions? Good. Okay, electrons are always moving. So at any instance, at any point in time, then it will have the polarized electron cloud. Then the other guy will also follow suit. And then this is the ID attractors. You can think of it this way, this is a lot more fleeting. It's a lot more passing, temporary. Whereas this is a lot more permanent. So guys, which one do you think is stronger? Just make a smart guess. Something that's temporary or something that's permanent? Okay, something that's permanent, right? Okay, so for here, okay, PD attractions are stronger than ID attractions. Okay, so far? Okay, the factor over here, right, I wouldn't say it's very important because I will come back to that recurring idea. Okay, but anyways, let me just discuss it. Okay, the factor affecting PD is the electronegativity difference. That's pretty much the only thing. Okay, so I can give you a very simple example. Okay, we have HF versus NH3. Who do you think has a larger electronegativity difference? Okay, HF, because why? F is more electronegative than nitrogen. That's pretty much it. Okay, so this is very simple, right? But why I'm not really concerned with this is because I need you to take note, it's also at the bottom of this page. When we compare our first factor, I'm just going to write it down again, I know it's on the board already, it's still your electron cloud size. That's how important it is. Whenever you compare two molecules, it doesn't matter whether it is non-polar or polar. You must compare the size first. Why? Okay, I know electron cloud size, we will talk about ID. Yes, but you all realize no matter whether you're polar or non-polar, you fundamentally have ID attractors. So if all molecules have ID, this should still be your first thing you compare. Make sense? Okay, but what if it doesn't work out? When does electron cloud size not work out? If the sizes are similar or same. So we will now go to our next factor. So we must take this down, this two-step process. When the first factor fails, then we can go to our second factor where we compare the different types intermolecular forces. In this case, we can use stuff like this. PD is stronger than ID, so it has a higher melting point or so on and so forth. But this is only if the first factor doesn't work. Okay, you only go to the second if number one does not work. Some of you all may be asking, why will it not work? In what scenario will it not work? Okay, later we'll see some questions. Okay, so once you have taken this down, okay, I need you all to look at page 47. Yes. ID. Okay, it's the exact same thing, but it's labeled as ID instead. Okay, because if you realize ID didn't start off like that. ID was initially very symmetrical. And then at any one point in time, then it will be distorted like this. The other guy will also be distorted. But because this was initially non-polar, right? That's why the interactions here are high.
Is it also?
I don't know, it still happens. Okay, this one was created in the instant. Instantaneous. Whereas this one is for a polar molecule, where the dipole is already there and will forever be there. This one was only created at any random point in time. Okay, ID is because, okay, fundamentally, right, all molecules have ID because that's like the basic interaction. You can think of it that way. Okay, so it's not really explained in this diagram because I know you all just see P, right? Okay, but no worries first. Okay, you all just need to know, right? ID is like the most fundamental interaction that all molecules have. PD is like an additional bonus interaction for polar molecules. Yeah. Okay. Never mind this diagram. You never need to draw this. It's just for your own mental image. Okay, but anyways, look at this flow chart, not flow chart, but this way of thinking first. Now we are going to take a look at the next page, this question here, page 47. Okay. Let's take a look at the question first. Can we see how we can explain this? Okay, so in this question, they give you facts, right? Okay, a lot of times, guys, in chem modeling, you are meant to explain the physical properties, right? Okay, I've mentioned that a few times. Our goal of studying interactions is to explain physical properties in real life. So, you will not be tested on predicting the boiling points, like who's the highest and who's the lowest. Most of the time, you'll be given a data like this, and you're supposed to explain that data using whatever knowledge you have. Because we learn a lot of different examples, right? We have learned a lot of different factors. Okay, we just need to apply the correct factor to this question. Okay, so how will you explain this question? What's our thought process like? Okay, so first of all, this is what some of you all may consider. The molecules, are they polar or not polar? Okay, polar because we have all the halogens, right? Okay, so to simplify this, we have this guy with a CCl bond, this is a CPr bond, this is a I bond. Okay, all are polar bonds, correct? Now the question is, when you see polar molecules, yes, they're all polar molecules. What's the factor that you use to compare? Okay, yes, good. Okay, so good. You all still know about electron cloud size being the primary factor. Okay, but this is what a wrong answer will look like. A lot of people see polar, they immediately discuss electronegativity difference. Let's see whether they are correct or not. Who is the most polar bond? Basically, the one with the greatest difference in electronegativity. Okay, yes, okay, the highest in the group is closer to chlorine already, right? So this will be the most polar. This will be the least polar. Most polar means what? Most polar means the PD-PD attractions are the strongest. Least polar conversely means weakest PD-PD. Okay, so are we wrong on any of the scenarios here? Okay, it's all correct, right? Polar one, not wrong. Polar, we look at the electronegativity difference, also not wrong. And we come to this conclusion, also not wrong. But is this correct for this question? It doesn't explain this question, right? If you go from strongest to weakest, the boiling point should have been decreasing instead, not increasing. So that's what I'm trying to say. You're not expected to predict because there are many factors. You can use any factor to explain, right? You're supposed to look at that particular data set and explain using the correct reasoning. And here, the reasoning is wrong. Because what you all did is you all never use electron count size first. That's a wrong way of answering this. So instead, guys, what are we supposed to compare once again? Mole ratio? No, not mole ratio. We should always be looking at. I haven't erased this statement yet. Electron cloud size is the first primary factor. Can see that? Okay, so we go down the group over here. What happened to the electron cloud size? Bigger or smaller? Yes. Okay, so let's write it down first. If the electron cloud size increases, what does that mean? A larger electron cloud is more easily polarized. If you're more easily polarized, that means your ID attractions are stronger. When you have stronger ID attractions, it means more energy to overcome. Does this explanation, does this version explain my answer? So does it explain the facts in the question? Yes. The boiling points here increases not because of PD-PD attractions, it's because of IB-IB. This question here goes to show that polar molecules like these guys do not just have PD-PD attractions. The IB-IB attractions here are in fact the reason why the boiling points are as such. So again, it depends on the question set. Whatever data they've given you, you must choose the correct reasoning. This is the reasoning that we use, not the previous one. That was wrong. Make sense? Okay, so this was the answer. Can so far? Okay, we'll slowly start to accept this. Okay, you can break this down first. All good. All good. Okay, with that said, we're gonna go to our next. Once we're done with, okay, we do a little bit first. Okay, because it's a little bit longer. We look at our third and last interaction. Maybe go halfway through this and then we take a short break. Okay? Right. So, okay, any questions so far? Anything you need to ask? Okay, do I have one? All right, let's look at hydrogen bonds now. Okay, as I mentioned earlier, we are looking at intermolecular forces today, not covalent bonds. However, this is called hydrogen bonding, right? Do not let the name fool you. Okay, it is still an interaction. Okay, so the word bonding is not literally like covalent bonding. Hence first. Okay, so what's hydrogen bonding? Okay, let me just throw out a few facts first. It's for polar molecules, but more specifically, the top three most electronegative elements, which is FON, F-O-N. Hey guys, you can think of it this way. F-O and N, since they are the top three, the elite, right? They will have their own league of its own. Hydrogen bonding. So as I mentioned earlier, think of it. Polar is PD-PD, that's like the normies, right? The peasants. But then, right, F-O and N are like the richest of the richest people. And because of that, right, they have their own league at the top, the elite club. This is the elite club, hydrogen bonds. In other words, you can think of it as hydrogen bonds, right, are the strongest out of the three elements. Because they're special, okay? It's more special than PD for like normal polar bonds. Okay, but PD is stronger than IB-IB. So this is the hierarchy. We're just getting stronger and stronger in this case. Okay. Okay, but this segment is a little bit longer because, guys, in order to enter an elite club, the criteria is a lot more strict, right? Does that make sense? Like you want to enter something that's more exclusive, you must fulfill certain criteria. Agree? So to enter the hydrogen bonding fan club, you need to be fulfilling two criteria. This criteria is very important. Now, guys, okay, to make sure you all don't get confused with 1 and 2, to form a hydrogen bond, you need two molecules, right? Remember, interactions are at least between two molecules, right? So molecule 1 and molecule 2, I'll call them M1 and M2. This right here is the hydrogen bond, correct? Now, each one of them needs to contribute one criteria in order to form this hydrogen bond. So I have molecule 1, it needs to fulfill something. Molecule 2 needs to fulfill something. So what a lot of people are confused with, right, is that each molecule needs to fulfill both. Okay, let's write that down first. Okay, each molecule only needs to fulfill one of the two. How do I phrase this? Okay, wait. Each molecule only needs to fulfill one criteria each. Okay, I think that's the best way to phrase this. In other words, if one molecule fulfills criteria 1, the other molecule must fulfill criteria 2. Okay, it's not molecule 1 needs to fulfill criteria 1 and 2, molecule 2 needs to fulfill criteria 1 and 2 also. Does that make sense? Okay, maybe I use a different term, criteria A and B. Okay, also can. Right, later we'll see the examples. Okay, but the first molecule must have a hydrogen, it's not called hydrogen bonding, right? bonded to F, hydrogen bonded to O, or hydrogen bonded to N. FO and N, okay, that's like the top three. You must have at least one of these bonds. And move on. Next. That's what molecule one needs to have. The other molecule must also have one of the elite club members, FO or N, okay, with a lone pair of electrons. That's the criteria to form one hydrogen bond. Make sense? Okay. The only way we can do this is to draw diagrams. So let's look at the hydrogen bonds that exist between water. Now let's check out, can water exhibit hydrogen bonding? Okay, water looks like this. Now if you want to form hydrogen bonding, you need to draw another water molecule, right? It's not just one water molecule. So perhaps let me just draw another one here. So this is molecule one, this is molecule two. Does molecule one fulfill the first criteria? Yes, it has an OH bond. Does molecule 2 fulfill the second criteria? Yes, it has an oxygen that has lone pairs. So you can definitely form hydrogen bonds here. Later I'll show you guys negative examples. Okay, but anyways, how do you draw a hydrogen bonding diagram? Okay, so I'll draw this in the box. Very important, because when you test this, it's usually 3-2 marks. But you need to be very specific. 3 things that needs to be fulfilled. Number 1, I need to see the partial charges. Number 2, I need to see the lone pair of electrons on FO or N. Number 3, then you label the hydrogen bond. Okay, remember, okay, I just want you to write a disclaimer. For the partial charges, it needs to come in pairs. I'll mention that in a bit. If there's a partial positive, there must be a partial negative. It can't be like only one of them. That's what I'm trying to say. Okay. So let's read this together. So how this looks like is the oxygen on molecule 2 must have a lone pair, right? So I'm just going to draw one of the lone pairs, that's enough. You make sure it's big enough so that examiner can see. If you draw very subtly, right, I'm scared that you overlook it. Okay, then what's next? It must interact with the molecule number 1, which has the OH bond, correct? Guys, you'll notice, because these molecules are polar, we have partial charges that look like that. O and H is polar, so the partial charges are here. The other guy also has partial charges, minus and plus. So currently I fulfilled criteria 1 and 2. Where do you all think criteria 3? Oh, yeah, not criteria 3, but where is the hydrogen bond between? Want to make a guess? Where the interactions are formed? Yes, okay. So you all can see, because this is partial plus, this is partial minus, they can interact with each other. So what you all need to do is this. H all the way to the lone pair of oxygen, you draw this thing here. And then you label this as your hydrogen bond. Again, this is not a covalent bond. This is an interaction. It's an intermolecular force. Okay, can? This diagram here, 2 marks. Make sure you have all the details written inside. Okay. We'll do one more page of this similar exercise and then we can take a short break. But anyways, you all can see why did I mention that they have to be pairs? Because as I've explained, the pair of partial charges must come first. Here they are partial charges, here they are partial charges. That's why they can form the interaction. Now, what a lot of wrong answers will look like is this. They will give me partial plus and partial minus, and then they ignore the rest. Now, this is wrong because you have to understand, right? It is the partial charges that come first before the interactions are. It's not the interactions form already, then you show the partial charges. Does that make sense? Interactions come after the partial charges are produced. Okay, anyways, just be a bit more kiasu. Okay, just draw as many partial charges as you can. Okay, then you will not go wrong. Hello. Okay, Ken? Okay, good. Okay, we're gonna try the same thing on the next page. Okay, then we can take a fast break. Okay, go over to page 49. Okay, of course, we will not be able to finish the notes by today. Just gonna cover a little bit more afterwards, then we can try a bit of questions really. Okay, so on page 49, take a look. I have this compound here called methanol. Okay, we try part A. Okay, I want you all to try this yourself. Okay, so we try to answer this first question. Can it form hydrogen bonds with itself? Yes or no? Okay, answer is no. Okay, I want you to highlight the words with itself. Basically, that's why I draw two of the same methanol molecules with itself, right? Okay, so if I want to draw another guy, and then we try to check for the criteria. Okay, let me just call this guy molecule. Okay, doesn't matter who's molecule 1 or 2. We look at the guy on the left first. What criteria does he fulfill? The first or the second criteria? Okay, he fulfills the second criteria because he has lone pairs of oxygen, right? So I'm going to call this guy molecule 2. If he's molecule 2, that means the other guy must be molecule 1. But does it fulfill molecule 1's criteria? No, it doesn't, because it still only fulfills molecule 2's criteria. There's no H bonded to O. That is the problem. So if both of them are molecule 2, there's no hydrogen bonding here. Okay, so to explain this, you can just very simply see there is no H bonded to O on methanol. Okay. Then you can consider part B now. All right, give you guys like 2 minutes to consider. Check the criteria 1 and criteria 2. Okay, you are supposed to ask yourself whether it can or cannot undergo hydrogen bonding first. Then later, if can, then you go and draw your stuff. If cannot, then never mind. Okay, so let's answer the question first. Can you form hydrogen bonding with water? See, across different molecules is possible still. And just not with itself. Okay, guys, before we do anything, I haven't answered this question just now. methanol only. So methanol with itself, it cannot form hydrogen bonds. So can I ask you all, what interaction does it have with itself? Okay, note this. Okay, note this down. Sorry. Okay, no idea. Okay, so if methanol cannot form hydrogen bonding, but it is polar, that means it's PDP is a normie basically. It's just a normal polar molecule, not the special type of polar molecule. So it has PD-PD attractions. Make sense? Again, you don't have to say it as both PD-PD and ID-ID. You know why? Because it's already assumed, right, that everything has minimally ID-ID attraction. So you can just tell me methanol has PD-PD and that's fine. You don't need to tell me that it's both because it's already implied. All right? Okay, anyways, okay, it can form with water because what criteria does methanol fulfill in this context? 1 or 2? 2. So you can label this as molecule 2. Shut up. Okay, anyways, water fulfills which criteria? 1. Now you notice, right? Methanol is forced to only have criteria 2, meaning to say water must have criteria 1. Okay, I know water can fulfill both criteria 1 and 2, right? But it's not, it doesn't have to care about 2 in this case. Make sense? Okay, let me just draw a diagram. Okay. Okay, lone pair of oxygen, partial charges. Okay, oops. Is this correct? Oops, forgot to draw the 4th one. Yeah, correct? Right? Okay, guys, take note. If you draw this, it is wrong. Very, very wrong. Why? There are a few mistakes over here. Okay, guys, you already mentioned, right, that the water must have criteria 1, nothing to do with the lone pair. The lone pair is supposed to be on this oxygen. Why is it not involved in anything? Right? Why is he not involved in the hydrogen bonding? That's one problem, right? What's another problem? There's many problems here. It's not labeled, okay. Okay, I just forgot to label because it's already wrong anyway. Yeah, but anyways, guys, you see, it's already wrong in terms of your criteria, right? Look at this bond here. Does it have partial charges in the first place? No, right? We mentioned CH bond is non-polar. You can't even have partial charges. Right? It's really wrong. Okay, a lot of things wrong about this, but it's because a lot of people see at H and O, right? They just put them together happily. Okay, please take note, must be very, very careful with this. Okay, you must know who is your criteria 1 and 2 very carefully. So let me redraw this once again now. Water is criteria 1. Criteria 1 must use the OH bond. Criteria 2 on methanol must involve this guy's lone pair. So that means it's like that. Very, very specifically like this. Partial charges here, partial charges here. You notice, yes, oxygen is more electronegative. This is correct. Okay, then you can label hydrogen bond. So take note of the wrong example just now. That one is very bad. Cannot. Okay, it's because that usually happens because you all don't know your 2 criteria as well. Okay? Any questions with this? All good? Okay, I know we've done quite a lot since the start of the lesson. Let's take a short break first. Okay, I know I didn't read, I just kind of like went through. Okay, we take a slightly longer break since it's quite a while. How was your COVID experience? How bad? Right, okay, good. So let's continue. Okay, we are going to talk about the last stages. We're still going to leave this here. Okay, but anyways, we just discussed hydrogen bonding. We only talked about how to form a hydrogen bond. Now we're going to look at the factors. Okay, the factors are what we're going to spend basically the beginning of the lesson. Factors affecting hydrogen bonding. Okay, let's take note of a few things. When we look at factors, right? Okay, we have to look at there are many factors so that we can encompass any type of explanation. Okay, so we look at the first one that's already written there. We can look at electronegativity difference, which is very, very straightforward. Remember, for hydrogen bonds, right, we only have possible types of bonds in hydrogen bonding, right? Okay, it's either HF, HO, or HN. So very clearly they have to affect our strength, correct? Who is the most polar out of all of them? Okay, very obviously HF, followed by all the way to HO. The least polar is HN, correct? So if I were to give you guys an example, the same example that I used just now, HF versus HN, so HF versus NH3. Who has a higher melting point? Who has a stronger hydrogen bonds first? HF, right? Okay, obviously then, yeah, okay, so HF has a higher melting point than NH3. Okay, that's fine. That's just a very simple example. Okay, so I'm going to give you guys 3 different structures, and I need you guys to try to arrange these 3 structures boiling points. Okay, now, I'm going to write it at the side here. For example, I have water, NH3, and HF. Guys, I want you all to arrange them in increasing order. Okay, so this is what we can theorize. This is our expected ranking. Okay, now our expected ranking is just based off the idea of electronegativity difference. Because I mean, fair enough, hydrogen bonding is only these 3 bonds, right? So we just look at this. This should be the only factor. Okay, so who has the lowest melting point out of the 3? Okay, NH3, simple. Okay, followed by H2O, and then finally HF. Okay, so this is what we expect. And the thing is, it's not correct. In real life, okay, this is not the correct ranking, because in actual fact, right, it's NH3, HF, then the highest is actually water. So that's the reason, right, guys? They do not actually ask you to predict the boiling points of compounds. What they want you to do is they'll give you the actual data set, and you're meant to find the correct explanation that fits the question. So that's what chem bonding tests you on. It's not to rank the things yourself. Okay, our job is to answer this. Why is it that our expected is wrong and our actual is like this? Okay, so first of all, HF versus NH3. Now, does this make sense using this factor? HF, NH3. HF has a higher melting point because it has stronger hydrogen bonds, right? Why? It's more polar than NH3. Okay, so that makes sense so far, right? Okay, so perhaps when we compare these 2 guys, we can still use the first factor on electronegativity. It works. But does it work when we are trying to explain why water is the highest? No. To explain why water is the highest, we clearly cannot use electronegativity. Okay? This is not viable. So that's why, guys, there are multiple factors to explain as many possibilities as we can. If we only had one factor, it is insufficient because clearly, right, water is an outlier. And that's why, to explain water, right, we're going to look at the second factor called the extensiveness of hydrogen bonding. This is what we're going to use to explain this. And we're going to go straight to this example, right, okay, which is in the question. Okay, so I know it's in the notes, okay, but I'm just going to explain on page 51. Go over to page 51. We are basically trying to answer this question over here. Okay, so to discuss the second factor of extensiveness, I'm just going to copy out the same 3 guys. Let's explain why the melting points are as such. Okay, perhaps the first thing that we want to explain is this one, right? Because this one we already learned. Okay, it's the first factor that we have discussed earlier. Okay, so let's just do that first. Okay, what's the first thing they need to tell me when you explain these 2 guys? Okay, electronegativity. Fluorine is more or less electronegative. Okay, good. So fluorine is more electronegative than nitrogen. So thus, the FH bond is more polar than the NH bond. So the first bullet point, right, is just to discuss the electronegativity and the polarity. Again, now guys, highlight keywords. So if FH is more polar, that means what? What's the next point to lead towards? Give it a try. FH is more polar. So, okay, so what? Stronger hydrogen bonds, exactly. Okay, but you can't just say the bond. Okay, you must not tell me the full molecule. HF has stronger hydrogen bonds than NH3. So if you have stronger hydrogen bonds, what's the next thing to explain? Okay, which requires more energy to overcome. Yes, good. Finish. Please highlight the keywords. You explain the factor, you compare the strength, last but not least, energy. I repeat. Factor, strength, energy. You might want to compile it into these three things. Factor, strength, energy. That's the flow for all these kind of questions. But this part, right, only seeks to explain the first two guys. Now we need to explain why water has the highest boiling point. We clearly cannot recycle the same factor. We need to use another idea to explain called extensiveness. So let me just explain what extensiveness means. Okay, the more hydrogen bonds one molecule can form, the more extensive. Can see that first. Okay, so let's take a look. For water, why is it more extensive? We're going to write down the answer first, then we'll explain why. Okay, in this case, why does water form more hydrogen bonds per molecule? Okay, perhaps, right? Okay, let's just draw the line. You can draw this elsewhere. Okay, how do I know how many hydrogen bonds a molecule can form? Okay, for that, right? Let me draw it up here. Let's look at NH3 first. And I want you guys to recall the two factors, the two criteria for hydrogen bonding. Can you remember what's the two criteria? We mentioned again. Molecule 1 must have what? Good. Okay, H must bond to F or to O or to N. What's the second criteria? Okay, lone pair of the electrons on. Yes. Guys, remember, you must have both of these criteria to form one hydrogen bond. So let's check. Criteria 1, how many NH bonds are there? 3 NH bonds. How many of the second criteria does it have? How many lone pairs are there on N? Remember? The shape of NH3 is trigonal pyramidal. It has a lone pair on top. So it has one lone pair. Guys, if you have 3 NH bonds and you have one lone pair, how many hydrogen bonds can you form? Remember, you need one each to only form one hydrogen bond. You can only form one. Can you see? The other extra 2 more NH bonds are useless because you need one each to only form one hydrogen bond. Agree? So that's how we know NH3 can only form one molecule per. It can only form one hydrogen bond per molecule. We try the same thing for the other two. HF. Okay, so that's what extensiveness means, by the way. Extensiveness, I can refer to this separate. Okay. You can later I'll give you guys more time to copy. Explain first. HF. Look at the first criteria. How many HF bonds are there? Obviously one, right? Okay, so if you have one HF bond, how many lone pairs are there on F? Okay, look carefully. How many lone pairs are there on F? 3. F has 7 valence. You have 3 lone pairs. But once again, how many hydrogen bonds will this allow you to form? 1. You can think of it as like a limiting factor, right? 1 hydrogen bond formed only. Make sense? So guys, you see between NH3 and HF, Can we use extensiveness to explain? No. They both are the same, so don't use the second factor. Use the first factor. You see what I'm doing over here? You look at the observation, you look at the question, and you see which explanation you want to choose. I choose the first one because the second one doesn't work. So it's all about choosing the correct factor. How about water? We know we can't use electronegativity difference. We try to explore extensiveness. Water looks like this. How many OH bonds? 2, right? Very obvious. How many lone pairs of O? 2. 2 lone pairs, 2 OH bonds. This allows you to form 2 hydrogen bonds. So guys, out of the 3, water is the most extensive. Think about it. One guy can form 2 hydrogen bonds. Then from 2, that guy can form all 4. Then 4 become 8. You see, very extensive, right? It's a network. Okay. Whereas this one is just 1 form with 1, form with 1, form with 1. Very boring. Very, very normal. But this one can keep branching. Can see that? So because of that, you'll definitely have stronger hydrogen bonds. 2, 4, 2, 4, 8, 16. Wow. Very, very extensive. You need a lot of energy to break this. So let's take a look at the second half of our explanation. We can continue over here. Water can form 2 hydrogen bonds per molecule. Okay. While NH3 and HF, so you lump them together, can only form 1 hydrogen bond per molecule. So you list down how many first, then you tell me water has more extensive hydrogen bonding. More extensive means stronger. And requires more energy to overcome. So see what's happening here once again. Let's highlight the keywords. More extensive, stronger, more energy. Factor, strength, energy. Same flow. The factor is just a little bit longer, but from here to here. Factor, strength, energy. This is the full explanation which will carry out to 3 marks. Okay. Once again, we learn multiple factors, so we can explain as many things as possible. In this case, that's how this question works. Okay, so basically, I always use this question, okay, to explain extensiveness. When you revise that time, right, you need to use these 3 examples as well. Okay, any questions so far? Okay, so I'm going to skip the second question because the one you all can answer yourself, because it's what I covered already. Okay, but I think there's a typo. Okay, so explain why HF has a higher boiling point than HCl, although what do you all say? Okay, change HF to HCl, although HCl has a larger size. I'm not going to go over this question. Okay, you'll try yourself. Okay, I just need to cover one more concept, which is question 3, and then we're done. Okay. For question 3, right, we need to look at, if we go back a few pages, we have a third factor that we can explain also. Okay, let's take a look at this third factor. It's a rather interesting one. And I would say this one mostly comes out at the later half of K1, but I cover first because I never know lah. Parai might even test this. It is more of an organic concept, but never mind. We cover over here. Okay. Okay, so last but not least, the third factor for hydrogen bonding, right, is this thing called intramolecular hydrogen bonding. This is possible. Any idea what intramolecular means? Intra means it happens within the molecule. Take note, huh? How about intermolecular? Between across molecules, right? So that's the difference here. We're going to see what this and how this looks like using the pattern that's given to us. Okay, I want you guys to label these two structures as okay, I know in the notes they swap, right? Okay, I think they drew this first. Okay, and then they drew this after. I want you to call the first one structure X, the other one as structure Y, just to make things a bit easier for us, because they don't have a name at the moment. Okay, I'll look at each structure, right? And just tell me what the difference is. Like the surface level difference. What do you notice? Guys, remember, when you're asked to compare the boiling points of two molecules, you must always look at what first? The first thing you must always compare. No matter what kind of interaction, what kind of molecule, you must always look at the electron count size first. Now, you look at these two molecules very specifically, right? Are their sizes the same or different? Okay, if you look at the MR, it's actually the same. The only difference is that they are on different parts of this ring, right? This is more organic. Okay, it's on different parts of the ring, different positions. So quite clearly, we can't just look at that. We can't look at size. Okay, but this has to do with hydrogen bonding because it's quite clear that O and H. Okay, so you can form hydrogen bonds with each other. Now, guys, can you tell me, right, which molecule will have this intramolecular hydrogen bonding? X or Y? Why? Yeah, why? Okay, good. You notice that they are so close to each other. So it's actually possible, right, for this H, because you need OH, right, to form a hydrogen bond with this oxygen over here. Okay, we don't draw the full diagram. I just need you to draw a little bit. And this right here is the intramolecular hydrogen bond. Why is it that X doesn't have this? Okay, it's like too far, right? Okay, so you can't like form anything between yourself. And I want you guys to know that this is a very tricky portion. Okay, because of a few things. Oops, okay. Okay, they drew this in a diagram as well. But I want you to take note. At the end of the day, when we discuss physical properties, here we're comparing the melting points. To reiterate one more time, physical properties are explained by what? How do we explain physical properties? It's right there, right? Intermolecular forces of attractions. Guys, we've been looking at the word inter, between molecules this entire time. Now, take note, every single molecule has an intermolecular force. But this guy here has an additional intramolecular hydrogen bonding. Can you see that? So take note, molecule X has intermolecular hydrogen bonds. So I can draw another molecule X and they can form hydrogen bonds with each other. But molecule Y has both intramolecular hydrogen bonds plus intermolecular hydrogen bonds. Can you see that first? Because if I were to draw two molecule Ys out, they can form hydrogen bonds with each other still. Agree? They still fulfill the criteria. But on top of that, it has intramolecular as well. Does this make sense? Okay. This guy don't have the intra feature. It's just can form with intermolecular forces. So what's going to happen here? I'm going to write down the explanation. I'm going to clarify some stuff. To explain this, okay, guys, Y has intramolecular hydrogen bonds. Just look at my wording. which causes its intermolecular force, its intermolecular hydrogen bonds to be less extensive. Yeah, I'm just going to pause here for a moment because this concept has caused a lot of confusion in the past, and I need to clarify this over here. Okay. Take note, every molecule has intermolecular hydrogen bonds. But this guy in particular has additional intramolecular. Now you will think that additional means it will be stronger, right? But actually no. If you have intramolecular hydrogen bonds, it will actually undermine the intermolecular hydrogen bonds. So look at the keywords. The main keyword here is the word cause. The intra causes the inter to be less extensive. It is a cause and effect situation. Okay? And we know less extensive means what? Weaker. Okay, so Y has weaker hydrogen bonds, which require less energy to overcome. So I'm going to write down these in short points. So Y actually has a lower melting point than X. Okay, this one is a slightly more complicated concept, and it's fine if you are not very familiar with this yet. Okay, because next time organic chemistry we will talk about this again. Okay, as I mentioned, it's a cause and effect situation. What a lot of people would do, right, would think is this. Intra is less extensive. I'm going to write this wrong one inside also, than inter. Wrong. Why is this wrong? Because you're not comparing intra versus inter. Every molecule has intermolecular forces. You must use it to explain your physical properties. Intramolecular does not explain its physical properties. So it's not an A versus B situation like here. No. It's an A causes B situation. That is the correct way of explaining it. You see that? So you are always leading back to inter. Because inter is the only thing that allows you to explain its physical properties, not intra. Complicated, yes. But hopefully, what I want you guys to take away from this is that when your school goes through this again, right, you must have this in mind. So you do not get even more confused in school. Because they will go faster, a lot less measured as what I've done over here. So bear this in mind. Okay? And hopefully when school goes through this, you will understand what's happening. And then explain to your friends also. Okay? All good? Anyways, this is not the most important part. I think the extensiveness one is still more important. It's quite content heavy, especially for hydrogen bonds. So far, any questions? If not, it's a little bit we've gone a little bit over the time already. Okay, that's it for today. Okay. Right. Okay, so yeah, next lesson, right? Okay, yes, I know today a lot of content. Try to read through before the next lesson. Okay, next Tuesday, same thing. Next lesson we'll finish up a little bit of pages, then we'll actually start tutorial. Tutorial we'll do in class and in homework. There's a lot of questions I want you to do, like a lot. Okay, yeah, that's it for today.